Eh bien, Alan, the stage is yours.
Bonsoir. Good evening. My name is Alan Kelly and I'm the R&D Director at NUMSCALE. And tonight I'm going to speak to you about a very interesting project I've been working on for the last couple of weeks, which involves FFTs and SIMD instructions. So at NUMSCALE we have clients in lots of different industries. We work with Zodiac on airplanes, we work with SNCF on trains, we work with Huawei on telephones. And because we work with lots of different architectures, we need tools that can help us become productive very, very quickly on these different architectures. So we work with smartphones, we work with embedded computers on drones, and we work with big servers. So for that reason, we developed two tools. We've developed bSIMD. Joël has spoken once or twice at the FRUG about the nuts and bolts of bSIMD, so I'm not going to go too much into that tonight. I'll just explain quickly that it's a C++ header-only library which provides a high-level abstraction for SIMD instructions. If you don't know what SIMD instructions are, don't worry, I'm going to explain in detail over the next few slides what they are and why they're so important. So also bSIMD, it provides about 300 vectorized map functions which replace those provided by the standard libraries such as std-cos or exp. But these versions are much quicker and in many cases much more precise over a wider range of elements. And our second product is Archer, and this is a multi-platform, multi-OS set of building blocks for applications in computer vision, machine learning, statistics, and image processing. And one problem which comes up again and again in each one of these areas is the Fourier transform. Our clients have often asked us, do we have a high-performance Fourier transform on different architectures? So I'm going to briefly explain SIMD because it's one of the important parts of this talk. So firstly, SISD, that stands for single instruction, single data. And this is the traditional method of programming. Each instruction acts on one chunk of data, and at the end of the instruction, it emits one result. With SIMD, single instruction, multiple data, each instruction acts on a chunk of data, in this case four chunks of data, and each instruction treats four chunks of data. So theoretically we can have a 4-byte speed up in this case here. So you can get up to speed up, as I said, of n on cache hot data. So there's lots of different types of SIMD. Back in the 90s, Intel advertised processors with MMX technology. Nobody knew what that actually was, but they advertised it as that. And since then, Intel have released many different versions of their SIMD instruction sets. So PowerPC and IBM have done the same, and ARM in your smartphone also has its own SIMD instruction sets. Question? So each generation of Intel processors have their own set of SIMD instructions, each one different. PowerPC and ARM. And the latest Intel processors, for example, they have 512-bit registers, so you can get up to a 64 times speed up with 8-bit integers. So if you have a really performance-critical piece of code, you really need to be using this. But it's a mess because, as I said, if you want your code to be portable and you don't want to learn the details of each instruction set, it's quite difficult. So for that reason, we developed bSIMD. So, and the main subject of tonight's talk is a Fourier transform. So what exactly is a Fourier transform? So does anyone recognize this device here that the football fan is blowing into? Yeah. So in summer of 2010, the vuvuzelas that annoyed everyone for a while. So at the World Cup in South Africa, they were selling these outside the stadium. So when we're sitting at home watching the football, this is the only noise we hear. We can't hear all the other noise of the stadium, and it's quite annoying. So the TV companies, they wanted to filter out this noise somehow. So how did they do it? So the Fourier transform is based on the principle that every function can be broken down into a sum of simple sine functions using this formula here. But what does that actually mean? Imagine I've put a microphone into my football stadium. This is the sound wave recorded by the microphone. This sound wave, it contains the normal noise of a football stadium, the noise of the football match, the fans cheering, and the vuvuzela. So I want to break this signal down into its constituent parts. I want to get the vuvuzelas, I want to throw them away, and I want to reconstruct the signal so we can watch the football and not have that annoying noise. So I break my signal down into, and I get, in this case, 3 different sine waves. So now I need to find out which one of these is linked to the vuvuzela and get rid of it. So if you analyze the output of a vuvuzela, it emits 2 different frequencies, 235 Hertz and 465 Hertz. So I go back to my sine wave. This one here is 265, this one here is 465. I get rid of them. I do my inverse Fourier transform, and I can watch my football in peace, or in my case, ignore football in peace. So, as I said, that's what the Fourier transform looks like. And using Euler's identity, this guy here, I can come up with a bit of C++ to calculate a Fourier transform. So we have 8 lines of code here. These 8 lines of code here have spawned a huge amount of research over many, many years. So if we look here, we have 2 for loops, each one from 0 to n. So, n squared. As computer programmers, we hate n squared, and we do everything we can to avoid it. So, what can we do about it? Back in the Cold War, the US government wanted to know if the Soviet Union was doing nuclear bomb tests underground. So one of the ways they had of verifying this was they had a network of sensors all around the border of the Soviet Union, generating huge amounts of data. One of the ways they processed this data was using a Fourier transform. But the techniques at the time, and especially the computers at the time, they weren't powerful enough to process this data. So James Cooley and John Tukey, they put their heads together and they came and they rediscovered independently a method which had been discovered by Gauss in the 1800s, and again in the 1940s. They actually discovered that the Fourier transform could be done in n log n complexity. So it's very simple. We take our original equation and we split it into the even and odd components. And we get this here. We can do this recursively. We do this and we take advantage of some symmetry in the twiddle factors. The twiddle factors are the sine and cosine, which come from Euler's identity. If you read any literature on an FFT, they're called the twiddle factors. Don't ask me why. So taking advantage of the symmetry in the twiddle factors and using this expression here, we can develop an n log n calculation for the fast Fourier transform. This is called a butterfly diagram. It's called a butterfly diagram because supposedly that looks like a butterfly. Right. So here we have a Fourier transform of size 16. So we have 16 in the vertical, but if we count here in the horizontal, 1, 2, 3, 4, log of 16 is 4, we have n log n. So this is called, as I said, this is called a radix 2 butterfly. And this is the main loop in an FFT. So how do we write a high performance version of this? N log n, and we're happy. So sorry, first of all I'm going to explain to you why the power of 2 transform is so important. So this expression that we've just developed, it only works for powers of 2 because we keep on dividing by 2 until we get to 1. But the power of 2 is the core of any Fourier transform. So the power of 2 is the core of any FFT implementation because a transform of any other size can be performed using this, using Bluestein's algorithm, for example. The forward and inverse transform use the same code, you just swap the real and imaginary components. And a real-only transform can be performed by packing it into a complex buffer of half the size. And for a 2-dimensional transform, so if we have a photo and we do a 2-dimensional transform, we do a 1-dimensional transform along each column, and then a 1-dimensional transform along each row. So if you implement a 1D Fourier transform correctly, you have everything else for free. So now I'm going to speak to you about the FFTW, the fastest Fourier transform in the West. This library turned 20 a few weeks ago, and it's a highly optimized FFT implementation for lots of different architectures. It's a feature-rich library, and to get the full performance out of it, it takes a bit of effort. You need to dig into the doc and play around with it a bit, and it's released under the GNU license. So some of you might recognize the tool clock, count lines of code. I launched this on the FFTW source code, and there's 300,000 lines of code. It's a big library. And if we look here, I've done some benchmarks. These graphs aren't very clear here, but I've done some benchmarks on each power of 2 from 32 to 16384 on my computer at work. And we see how the FFTW scales. On the y-axis here, we have the number of cycles per element. So this takes between 4 and 8 cycles per element for an FFT between 32 and 16384. So if we take 2048 as an example, that's roughly 5 cycles per element, 6 cycles per element. And if we go back to our double for loops here, anybody want to take a guess? I benchmarked this on my computer too. Anyone want to guess how many cycles per element? 60? 600? Sorry?
Did it finish?
It hasn't finished yet. No, in reality, it's 181,000 cycles per element. So the FFTW people have done their work. That's 30,000 times slower. So I could do some of my normal optimization tricks. I could pre-calculate the sine and cosine because we reused them. I could do the complex multiplication manually and maybe gain a few cycles there, but I'm not going to gain it times 30. So the challenge: write a multi-architecture, lightweight and high-performance FFT and be competitive with the FFTW on all architectures, and all this in several weeks. It's not ambitious. So we're going to be working with 4 different architectures. We have ARM, 32 registers, is 32 SIMD registers with 128 bits per register. Power 8, we've got a massive 64 registers, again 128 bits per register. We have Intel's KNL, we have 32 registers at 512 bits per register. And we have a normal x86 computer, your laptop, your computer at work, has 16 SIMD registers at 256 bits per register. So we want to write a generic code which is optimal on each one of these architectures. How can we do that? So the reason why I speak about the number of registers is it's very important, because the more data you can fit in your CPU registers, the higher performance you have. If you've got data in your L1 cache, it can take 3 or 4 cycles to transfer that data from the L1 cache into a CPU register. So if you can stock lots of data in your CPU registers, you've got a massive performance boost. So back to our butterfly loop here, and I'm going to show you how to vectorize this using SIMD instructions. So if I write this code on ARM, we have with ARM intrinsics, if I follow the ARM doc, this is the code I end up with here. I use the type float 32 times 4, and this is the code I end up with. How about IBM Power 8, or in this Intel AVX2? So for my office computer, I have a type MM256, and these are the instructions I use. For Intel's KNL, their latest processor, I have a different set of instructions. And finally, IBM Power 8, again, I've got a different set of instructions. So I've got 4 sets of code here, and I only want 1. So how can I do this? I'm going to use bsymd, and it's going to use its register abstraction. I've got my type here. It's a pack which is templated on T and N. T is the type, and N is the number of elements. If you do a pack of just type T, so a pack of float, that automatically picks the best type possible for the computer you're compiling on. So if I write my code using bsymd, this is my code. I've got my operators overloaded. I've got a nice, clean, readable code, and this generates the exact same code on each of the 4 architectures had I written my code by hand. So the next step, if I want to get a bit more performance, I need to unroll my loops. I want to use as many registers as possible. So also, another reason unrolling works quite well is each CPU instruction has a certain latency. Some instructions complete in 1 cycle, some instructions take 5 or 6 cycles. So if I can do 5 instructions of the same type, one after the other, with independent data, I'm going to get a big performance increase. So I unroll my loops. So I get this code here, I unroll it, so I copy paste my code, change the names of my variables, and hope I haven't introduced a bug. So I might want to unroll by 2, by 4, or by 8. I don't know, I need to try them all and test. How could I unroll in a generic manner? So with bsymd, I have a hash defined for each architecture. This is my only architecture-specific code. And I tell my pack on ARM I want to unroll by 2. On PowerPC, I've got 64 registers, so I unroll by 4. On Intel, I only have 16, so I don't unroll. And on AVX512, the KNL, I want to unroll by 2. What does my unrolled loop look like? It's the exact same. This is automatically unrolled. So what does this generate? On ARM, I OBJ dumped my code. and this is what I ended up with. I see I've got my vector instructions here. I see my registers, they begin with V, and there's no traces of BSIMD here. I've just generated proper ARM vectorial instructions. On the Intel KNL, I've got my ZMM registers here. These are my 512-bit registers. Again, only vectorial instructions, no traces that I used a tool to generate this. Power 8, exactly the same. I've got my V registers here again. And AVX2, I've got my YMM registers. So there's no traces of what I've used a tool to generate this code. So back to our butterfly loop here, and there's one final problem. So if I've got a big Fourier transform, I can easily vectorize this part of the loop here. If I've got a vector holding 8 elements, when I get here, it's quite difficult to vectorize because I need two data points which are in the same vector. So to deal with this problem here, I need to shuffle data between vectors. How do I do this? So with BSIMD, I can simply shuffle my vectors. I've got a shuffle function. So I've got 2 packs, which again are just the BSIMD type for a SIMD register. And I call my shuffle instruction here. I want all the even elements in my vector. I want all the odd elements. So this is going to print 0, 2, 4, 6, 1, 3, 5, 7. It's exactly what I want. How about I've got an AVX machine with 8 items in each register? What happens? I need to write my code like this. Or what if I've got 16 in each register? This is getting annoying, it's long, and it's not generic. So I can use some constant express functions. I could also do some metaprogramming, but if you've ever done metaprogramming, you realize that it's more painful than going to the dentist. So I use my const express function here. I pop it into my template here, and then no matter what architecture I'm on, this will generate the right pattern for odd and even. So I do my shuffles correctly, and I can continue with my FFT. Another operation I need to do, I need to take the first half of 2 registers and the second half of 2 registers. So I write my 2 const expression functions here, pop them into my template, and again, I get exactly what I want, the first half of my 2 vectors and the second half of my 2 vectors. So let's look at performance. We write this code, and I benchmarked it against the FFTW. So Archer, the FFT is in blue, and the and the FFTW is in red. So on ARM, you see that it's equal to or less than on every single size. The performance is better with the NUMSCALE FFT than FFTW on ARM. How about IBM Power 8? It's much the same story here. It's up to 2 times faster. On Intel x86 AVX2, so your standard laptop, we have Archer FFT here and FFTW here. So we see all except for the 2 smaller sizes, the FFTW is faster than Archer FFT, which is normal when you think about it because this is hand-optimized code versus generic code. So with a normal FFT implementation, you need to specialize for certain small sizes. And I think you can guess which sizes I specialized for here. And finally, the Intel KNL. So for half the sizes, it's quicker, and half the sizes, it's slower. So at this point here, I have no idea what it's doing there. So again, NUMSCALE wins on half of these, and it's slower on the other half. But again, this is a generic code versus a hand-optimized code. So earlier on in this talk, I launched count lines of code on the FFTW, so I need to do the same on my FFT. 653 lines of code versus 300,000 lines. So I'd like to thank you for your attention and invite you to ask any questions. On peut faire les questions en français si vous voulez.
So generosity is very nice, but it doesn't explain the performance increase. I mean, what prevents FFTW to write exactly the same loop as you did with Intel intrinsic? They should get the same result. And I'm surprised that you get some type of factor of 2 while not doing something from what you presented that doesn't look natural.
Yeah, well, I looked at the algorithm and I followed each logical step by step. But as you can see on Intel, the FFTW is faster. So I'm guessing somebody sat down and took a long time to figure out the right order of instructions to gain that performance boost. So I'm also guessing on the other architectures that somebody hasn't spent a huge amount of time optimizing the code.
And another question that may answer the first question, but I don't know. You're manually tuning the unroll factor. That's something a compiler should be doing better than you do. So why didn't you rely on the compiler to do it? Why not using a pragma unroll to let it decide the good unrolling factor? Because it knows how many registers it has, so it should be able to make better decision than hand.
In theory, yes. My experience with that is, in fact, doing the hand unrolling yourself works better, especially in the SEMD case. So just experience tells me that to try the different options, and benchmarks is the only answer I can give you to that. It goes faster when it's done like this, so that's why I do it.
I think the point is that the compiler is more tuned to know how to optimize and / enroll code with scalar operations. And I think that as soon as you start writing your own CMD26, maybe just say, okay, you're doing whatever you want to do. I don't want to look at that. That's one of my, hypotheses. I don't know. I mean, but this may explain that. If we had someone writing compiler in the room, it may maybe give us. Alors je pense que oui, c'est un effet qu'on a remarqué souvent, c'est que dès que tu fais des choses un petit peu trop smart, le compilateur, il n'a pas vraiment envie de faire plus smart que ça. Mais je vois que Arnaud a quelque chose à dire.
One of the first things the compiler tries to do is to re-roll your loops, in many cases. So developers and compiler developers have been fighting because a long time ago it was better to unroll because compilers were not able to understand the loops. Now they are able to understand the loops. That's how you can construct vectorized code. So my point of view is that maybe the compiler is not yet ready to do all the vectorization you would like to do. But the way to expose the parallelism to the compiler is with the loops. And then, especially on ARM, you need to take into account that you can have many different implementations. And the compiler can take into account the number of registers, the pipeline, whether you have out of order, register renaming, and all this you don't have with a manually unrolled code. So yeah. You may at the moment reach the peak performances, but your code is not portable over time.
Yes, that's true, but there's nothing stopping me sub-defining my ARM architectures. If I want to say I've got a certain smartphone on another phone that I want to compile for, there's nothing stopping me calculating the right unroll factor for each. It's a case of running a few benchmarks, a couple of minutes work, and I tell it the unroll factor. And if the day comes that the compiler does a better job from me, I delete that code and I'm happy.
I think you noticed that FFTW is a generated code library where the main code is from OCaml. So you have base code in C, which is the driver, and all the interesting parts is generated from OCaml. And the interesting thing about FFTW is that they essentially built a compiler optimized for FFT in OCaml. They do smart things like on the butterfly graph, they transpose the graph, simplify the graph, and transpose back in the graph. And by that mechanism, they found some interesting pattern to optimize performance for certain kind of FFT and certain kind of lengths. Did you try to follow these guidelines or this kind of optimization at your level to get the same performance boost they got from OCaml?
So I looked a bit at the FFTW code for some inspiration, but I found it quite difficult to follow, so I didn't spend too much time on it. I also read some papers on the FFTW, but again, I didn't have a huge amount of time to do this, so I didn't have a huge amount of time to look at all the available resources. So I looked at what I had, and with a pen and paper, I derived the algorithm that I ended up using, and I implemented that, and I tested it. So I'm sure there's many better ways of doing it than what I've done. I'm just presenting what the best solution I found so far.
Okay. And just to be fair, the line count for FFTW is mainly the OCaml count. The rest of the code is mainly generated.
Okay, I need to go back to that slide there. I just quickly downloaded the FFTW and ran clock on it. I didn't think too much about it. Let's go back to where are we? Here we are. Okay, so OCaml, we have 5,400 lines of code. Okay, that's very impressive. I didn't realize that was the generator of the FFTW. That is very impressive. So that's the OCaml compiler for FFTW. Okay, that's very impressive.
In the GenFFT subdirectory in the archive.
Okay.
So did you try to implement the same thing with just for loops with static bounds? Because we know that for loops are vectorized now automatically. So did you try to?
Yeah, my first implementation was with for loops, and the performance was a long way from. I forget the exact figures. It was much better than 180,000 cycles per element, but it was still probably a factor of 10 out.
And they were vectorized, or?
When I didn't vectorize the code, it wasn't auto-vectorized by the compiler. I was using Clang 6.9 or 3.9 and GCC 6.1, I believe, and neither of them auto-vectorized that.
Okay, so thanks for the question. Thanks, Alan.
And thank you.